I want to talk about Lie algebras. Oftentimes, Lie algebras are motivated from Lie groups, and their study, yeah, normally motivated that way. I'm not going to do that in this video because I'm not going to expect you to know what a Lie group is, because I'm not going to expect you to know what a manifold is. Maybe we'll jump in there, but this is going to be an introduction to Lie algebras that doesn't depend on that. So what is a Lie algebra? Well, throughout, the theory is not very different if you deal, well, I shouldn't say that. A lot of what I'm going to say works just as well for any field, but I'm going to let K stand for the real numbers or the complex numbers. Pick your favorite. We're probably going to focus on this mostly, but even if you just wanted to study one or the other, actually, the theory of both of these things kind of informs each other, so it's worth knowing about both, and we'll later see the interactions between those. So, what is a Lie algebra? Well, before I even give you the general definition, we should probably talk about some examples ahead of time, right? Because why do we make a definition, an abstract definition? It's because we notice similarities between certain structures in mathematics, and we then try to codify those similarities with a definition, right? And then once we have that definition, we can sort of study the abstract general properties that apply to those terms, right? So, if you studied matrices at any point, which probably you shouldn't be watching this video if you haven't studied matrices, but I'm not the boss of you. Watch this video anyways. So let M sub n, right? This will be the over K. So K is the real numbers or the complex numbers. This is just the set of n by n matrices, right? And one thing that's important is whether two matrices commute, right? So it does xy equal yx or not. There's a lot of interesting things about this, right? It was probably the first time a lot of people encounter something non-commutative like this. It's matrices. And there's implications for matrices being commutative, right? If you've done some more advanced linear algebra, you know stuff about maybe simultaneous diagonalization. Maybe you've heard about that before, maybe not. It's fine. Um, but there's also, we might just talk about like the operations in which we do something, right? Classic real world example of non-commutativity, putting on your socks before your shoes or putting on your shoes before your socks, right? Two very different outcomes. Um, so in order to another, we can just rearrange this a little bit, thinking about a little bit differently. Um, if xy is equal to yx, that's the same thing as xy minus yx being equal to the zero matrix, right? And so a shorthand we use for this expression is sometimes these square brackets. So we would say xy. We're going to define this to mean xy minus yx, right? So now we get that the bracket of x and y is equal to 0 if and only if x and y commute. Okay. And so let me point out some properties that this bracket satisfies. And at first, it might seem a little bit silly. But nonetheless, uh, uh, let me point out to you that x, bracket x, is equal to 0, right? Because if I plugged x in here, that just is x times x minus x times x. So that's 0. The other thing is that xy is equal to, well, that's xy minus yx. Rearranging it slightly, that's negative y, negative yx minus xy, all with parentheses around that. And that is just the negative of the bracket of yx. And the last one, I don't feel like writing out, so I'm going to leave it to you to verify. It's that x bracketed with y bracketed with z plus y bracketed with z bracketed with x plus z bracketed with x bracketed with y is equal to 0. Okay, big whoop. You might say, right? That's okay, fine. These are going to be important for us in a moment. Let me point out, so this actually gives us a whole infinite case of examples. So here are the things that are important. I have my n by n matrices, right? By the way, this is also a K vector space, right? I can multiply my matrices by scalars from my field, being the real or complex numbers, and I can add them together, and that scalar multiplication distributes over the addition nicely. It's a K vector space. So I have a K vector space. I have this bracket that satisfies these three properties, and it's also what we would call bilinear. So what that means is you remember, a linear map satisfies something like this, right? So I have one argument, and it's linear in those two arguments, which means that it respects my scalar multiplication as well as my addition, right? But now in my bracket, I have two arguments, right? I have an x and a y, and these are both vectors in my, well, they're matrices in this case, which means that they're both vectors in my vector space. And I'm going to demand that, if I just sort of held my hand and covered this thing up, I'm going to imagine that this argument is linear, and then separately this argument is linear. So what do I mean by that? I mean that if I had some real numbers, complex numbers, whatever field you want to take, what's going to be true is that ax plus bzy, right? It's going to be linear in the first component. So that means not only can I split up this sum, but I can bring my little scalars out in front. So this should be the same as axy plus bzy. And the exact same thing should be true in the second component. So if I had x, c z plus dy, well, that should be the same as c xz plus d xy. Boom. So these are all the properties. I have a vector space, my matrices. I've got this bracket thingy that satisfies some seemingly obscure, okay, whatever, some random facts. And it's bilinear. Well, this you might, at least if you've done linear algebra, you can maybe appreciate that more immediately than these other things, although certainly the bracket itself, again, tells us something about the commutivity of these objects, right? Here's a cool thing that's very similar. Consider the R3, the real numbers. Notice that this 2 is a vector space. I'm going to define the bracket of two vectors in this vector space to be the cross product of those vectors. Now notice the cross product of a vector with itself is the zero vector. Notice that if you take the cross product of two vectors and you flip the positions, it's the negative of the you pick up a minus sign. And well, this last one, guess what? It's also true. But again, I'm going to be annoying and just let you go through that algebra yourself. Just, very carefully from the definitions, you're just going to have to write out, all of these things with the cross product. And last but certainly not least, the cross product is bilinear, right? So if I have some vectors, A, U plus B, V cross W, this is the same as A, U cross W plus B, V cross W. And same thing with the second component. So what do all these things have in common? Well, you probably realize where I'm already going with all of this. These are both examples of Lie algebras, right? So matrices together with this thing that captures the idea of whether or not they commute, as well as the cross product, which is pretty important idea in just linear algebra, geometry in general, and certainly in physics, right? Angular momentum, it's all cross products. So putting those two things together, we're going to say that a Lie algebra is a K vector space. And I'm going to write it as, that's my way of writing mathfrak G, which is common notation for a Lie algebra. So a Lie algebra is a K vector space G together with a bilinear map, which we call a Lie bracket. So that takes in pairs of elements and returns something in your underlying vector space, as in the two examples, such that, well, I'm not going to rewrite all of them, such that exactly these three conditions happen, right? I mean, of course, this doesn't make sense anymore, like if I'm not talking about matrices, right? Like I don't necessarily have multiplication, so and let me get rid of the cross product. But so whatever my bracket happens to be, because there could be some wild and wacky definitions, as long as it satisfies this, and this third condition, which is often called the Jacobi identity. Right? And so probably there's a good reason to study this, right? Comes up in our understanding of 3D geometry, comes up in our understanding of matrices. So these two things are similar. If I prove some abstract theorems about anything that satisfies similar conditions, I'll get more mileage out of it. I'll learn something about n by n matrices and the cross product simultaneously. So fantastic. We're saving ourselves some time. Okay, so that's what a Lie algebra is. Now, I know I already gave you some examples, but let's sort of think like a mathematician. Let's try and cook up some examples, right? And the first thing you always want to do is, so, we want an existence proof. And I think the way a mathematician thinks is well, let's find the most economical existence proof first, right? So always find the stupidest example you can and see if you can come up with, so-called degenerate examples. So what would the stupidest example be? Well, I need a K vector space, right? So the first thing to think of is, what is the stupidest vector space? Well, it's the zero-dimensional vector space, right? So it's just the vector space that has a single vector, right? I don't have any smaller vector spaces than that. It truly is the stupidest. So I need a bilinear map then on this vector space. So it needs to take in a pair of vectors and spit out a third one. Well, I only have two vectors, so all I need to do is tell you where these two vectors go, and there's only one choice of where they can go because this vector space only has one element, so I have no choice. If there is a Lie bracket, it has to go here. Again, I'm gonna leave the verification of all of these properties to you. Well, I mean, this basically already verifies the first property, right? That for all x in the vector space, the bracket of x with itself is 0. We checked all x, right? There's only one. It's just the 0 vector. And the symmetry property as well, right? We want to show that should have put my qualifiers here. All x in V. I want to know that for all x in Y in V, x, y is minus yx. Again, I can't even take a different x and y, right? These are the only x and y I can put here, and the negative of the 0 vector is the 0 vector. We're done. Finally, it should be pretty quick to convince yourself that the Jacobi identity holds, right? I mean, everything is 0, so each of these terms should go to 0. Again, to be formal and rigorous and precise, write it out yourself, but we can see, yeah, great. Okay, so we have a Lie algebra. In fact, we've discovered the stupidest Lie algebra that could possibly exist. Just because it's stupid doesn't mean that it's unimportant, right? The trivial group is very important and shows up in a lot of different places. Life would not be the same without the trivial group. So just because something is stupid doesn't mean it's unimportant. A Lie algebra. So here's another way that a mathematician might think. Okay, we found the sort of stupidest, more degenerate case. Now, let's think about this. A Lie algebra it's a vector space, real complex numbers. It's a vector space, and then we put this bilinear map on that vector space, right? So another question you might ask yourself is, well, if I think about all the Lie algebras that exist, do all of the vector spaces show up? Well, by that I mean up to isomorphism of vector spaces. Oh, and this reminds me, you should all be typing angrily in the comments right now because I broke one of my cardinal rules, my own philosophy. Well, I certainly didn't come up with it, but there's an idea that, you should really get angry at someone if they claim to define an object for you, but they don't claim to define what the maps between those objects are that you should care about. Why is that? Because I can give you a definition of an object, right? And I can give you here's the things that it satisfies. But if I don't tell you what the homomorphisms should be, then that doesn't really tell you what you should care about that object, right? Because in general, in math, the homomorphisms are the structure preserving maps. And we care about preserving structure. So if you don't know what the structure preserving maps are, you don't know what the structure is that you care about, right? So for instance, groups, like the thing that makes a group is that multiplication operation. And your homomorphisms preserve it, right? The thing that makes a vector space is its linearity, right? Which is why the thing that we care about between two vector spaces, those maps, those functions, are the linear transformations. So in a similar way, in order to complete the definition of a Lie algebra, I should tell you that a homomorphism of Lie algebras is, well, my Lie algebras are, on top of everything else, K vector spaces. So probably, if that's, part of the definition, if it really is something I should care about, I should demand that my homomorphism is K-linear. So let's say phi between two Lie algebras, G and H. If this is going to be a Lie algebra homomorphism, it better respect that vector space structure. So it should be a K-linear map. And now what's the other thing that is part of my Lie algebra? Well, it's this bracket, right? It's I have this bilinear map, right? So what should that mean? How should my homomorphism interact with that? Again, let's go back and just think about all the other algebraic structures you might know about. Vector spaces, groups, rings, maybe, right? It basically says if you've got this operation, it shouldn't matter whether you do that operation before or after you apply the map. Formally, that should say that for all x and y in my Lie algebra G, if I were to take the bracket of x and y, I'm going to put a little subscript g here, so you know that this is the bracket associated with g. And then I were to apply, so that will give me back some element of g. So then I apply my map to it. Then that should be the same thing as if I had first applied my map phi to each of the elements x and y. And then, so both of these are now elements of my Lie algebra H, and then taking the bracket of H. So this is a homomorphism of Lie algebras. And now only now have I officially completed the definition. By the way, let me say, if presumably about vector spaces. Otherwise, you're probably very confused at this point. And I'm going to assume that maybe you know something about, you've studied groups and you studied rings before. Okay. And I'm going to make a little table here. Again, now that you know what a homomorphism is and you're familiar with other algebraic structures, as a mathematician, you should start asking yourselves, well, what are the similarities here? So what I mean by this is, we have, what are our subobjects, right? In vector spaces, we have subspaces, right? In groups, we have subgroups. And in rings, we have subrings, right? So, well, now I've got Lie algebras, right? Is there a notion of subalgebra? Well, don't wait around for someone else to tell you whether or not that notion exists yet and if it's worth studying. Ask yourself, what is the right definition? Right? How would you, so look up, if you've forgotten, look at vector spaces, groups, and rings, look at subspaces, subgroups, and subrings. And with those things in mind, knowing that those are interesting and useful concepts, you should ask yourself if a similar thing might be useful and interesting for Lie algebras. And you should ask yourself, without looking it up first, what do you think the right definition is? And only after you've written it down on a piece of paper should you go and look up what other people have decided is the right definition. Not only are there sub-objects, but there's things. Let me change color. There's things to quotient by. So with vector spaces, you can quotient by just any subspaces. With groups, you have to take normal subgroups, right? Those are the only ones that make sense to take quotients of. And with rings, you have to take quotients of ideals, which aren't even rings. Well, depending on definitions, I'm going to assume that we're all dealing with rings with unity. So again, you might ask yourself, well, can I take quotients of Lie algebras, and what would be the appropriate definitions for the objects that I can do that with? So that also leads to, an idea of kernels and images and the first isomorphism theorem. These all exist in vector spaces. These all exist in groups. All right, first isomorphism theorem. These all exist for rings. Is it true for Lie algebras? What else can we ask ourselves? What about commutative objects? Well, we literally started this idea with talking about commutivity, right? And somehow, like, the bracket being 0 is our idea of commutivity, right? So again, all vector spaces are in some sense commutative. Here, for groups, we had the notion of abelian groups, and we have the notion of commutative rings, right? We also have, building on this, the commutative sub-objects. So internal commuting structure, we might say. Again, this is just all subspaces, or I should say, the things in your object that commute with everything else, right? With groups, we had the center of the group. With rings, we also have the center of the ring. And again, ask yourself, what's over here? What's over here? Let me just point out a couple more things. You already get where I'm going. So hopefully you can start predicting some of these other things on your own and start asking yourself these questions, right? The last one I want to say is the largest. This is maybe less familiar depending on how much experience you have, but the largest commutative quotient. So again, vector spaces, this will just be, the entire vector space you start with. For groups, we have what's called the abelianization, which is your group quotient, what's called the commutator subgroup. And this also implies the existence of some sort of commutator sub-object, right? So I'm just going to leave question marks here and question marks here, and I want you to think about those things. So think about all of these concepts and try and write down a formal, rigorous definition yourself and see if you can come up with some examples based on the previous examples of like the cross product and matrices. Yeah, see what happens. So before we take off, do I want to say anything else? Yes. So continuing to think about a mathematician, right? So we found we have the most degenerate, the most stupid, but still highly important Lie algebra. Another question is, well, is every vector space the vector space of a Lie algebra? right? So remember our definition in terms of objects, a Lie algebra is a K vector space together with a bilinear map such that blah, 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 blah. So if I write down all the Lie algebras that exist, and I look at the vector spaces that show up in those definitions, do I see every real and complex vector space? Well, and we're mostly going to focus, actually, no, we'll talk about some infinite dimensional stuff as well. Um, hopefully that doesn't scare you off. So let's try and answer this question, right? What is the most the most stupid Lie algebra, or is every vector space a vector space of a Lie algebra, right? So let K let V be a K vector space. And again, we're just trying to, yeah, we want to find non-stupid ones, right? We want to find interesting ones. But so now the goal is, first, again, it's just a proof of concept thing. Can you find a Lie bracket on this vector space? All you know is that you have a K vector space. Can you define a bilinear map such that for all of your vectors, V bracketed with itself is the 0 vector, U bracketed with V, sorry, those both look like V's, is the negative of V bracketed with U, and such that it satisfies the Jacobi identity. So actually, this is where I'm going to leave the video. I'm gonna make you think about it for next time. And again, I encourage you, come up with the stupidest one that you possibly can, right? Don't try and make it complicated. I mean, you don't have a lot of options because all you have in your hand here is an arbitrary K vector space, right? So I'm going to leave you with this, and I will see you in the next video.